All right, let's go ahead and get started. I'm sure you're all aware of where you are. We've had 2 wonderful days before this, thanks to the previous chairs. This is the management techniques in encrypted networks. We'll remind everybody we are recording this for later use. I think we all know the goals at this point, and so I won't go over them in detail. The important thing that we are now at is day 3, which is, previously we discussed sort of where we are, what the state is, and, where we want to go. And the real question now is, well, what do we do? How do we get there? And I think a lot of some of yesterday's talks actually, dived into this too. Where we want to go and how do we get there do kind of overlap quite a bit. And that's just fine. So we're going to start today with a presentation by Michael Collins on improving network monitoring through contracts. And another one by Paul Grubbs on zero-knowledge middle graphs, and one by Tommy Polly on Red Rover collaborative approach to content filtering. There's a fair amount of space, especially because this is the last day of the workshop. I really didn't want to fill it with too many presentations because I think we need a good discussion at the end. And we'll sort of divide it into 2 parts a little bit. Well, I have a lot of space for the talking about what comes out of today's presentations and topics, but I'm hoping we'll do a little bit of workshop wrap up too and think about stuff as a bigger picture and maybe next steps and things like that. So with that, I'm going to go on to Michael's presentation.
Thank you, Wes.
Yep, you do not have there it is. You do not have animations, correct?
There are no animations. I am not that exciting a presenter.
All right, you should be able to see your slides, yes?
I see my slides.
You're good to talk.
All right, so hi folks, my name is Mike Collins. I'm a researcher for USC ISI. I'm on the opposite coast from West. I'm on the opposite coast from West, and I'm on the opposite coast from Wes. Before I came to ISI, which is about 2 years ago, I worked for a company called Red Jack, and before that, I was at the CERT at Carnegie Mellon University. A lot of my work there was in large-scale network monitoring, primarily for the Department of Defense. So if you've ever heard of Centaur or Silk, I was heavily involved in building those. And if you've heard of Einstein, I can claim no culpability for that whatsoever. So in terms of what I was going to talk about today, next slide, please, Wes. Okay, so I want to talk in particular about this concept of a network contract. Now, I believe the core idea here, which is to have assets publish a behavioral envelope, we've talked about in various ways in presentations over the past few days. So I'm going to slightly change the angle of how I'm talking about it to focus on, in particular, the role of security operations in this and the idea of human in the loop, because I think we've talked a fair amount about automated publication. And I think one of the core things when we're talking about security is we're dealing with, for lack of a better term, the problem of hostility, which is to say that we are going to see not only unexpected but very bizarre traffic run intentionally to mess with us. So the core idea, and said that I found the discussion about MUD yesterday, in particular View Revolution, about this, is we would have a traffic descriptor. But the goal in this case is the descriptor enables operators to focus their attention on unknown or suspicious behavior. The key part of this is the idea that the contract would have multiple states. So the system can say, for example, this is my behavior under baseline circumstances. This is when I need to do a software patch. This is what my behavior might look like in an emergency. So the reason for this, a lot of what drove me in building this was ideas that came from Nancy Levison, the author of Safeware. She's a non-traditional reliability researcher. And in particular, her sections on monitoring reliable systems in that book are, I think, very insightful. And she talks about the need for monitoring systems to support crises and for monitoring systems to help develop expertise among operators so that they get a deeper intuition of how systems operate under normal and abnormal circumstances. Next slide, please. So, as part of this, I've been working for the past few years on what I call attention-based response. Now, the idea of this is if you take a look at the history of sort of security operations and intrusion detection, for many years the operators were considered a kind of appendage to the IDS. And certainly when I was in my previous job, I did run into situations where I would talk to people, C-suites, whose primary goal was to figure out how to get rid of operators. The idea of operators having expertise and having their own independent agency, I think, is a relatively recent concept. And I would say the division point is MITRE a couple of years ago wrote a book called 10 Strategies for a World-Class Cybersecurity Operations Center. And one of the points they make there is that when SIM, sort of our baseline monitoring software, was introduced, the first response of most organizations were, great, I can automate this and get rid of all of my analysts, and then realizing, oh, there's an awful lot more hostile stuff going on my network than I expected. I'm going to need more analysts. And what this and as this sort of acknowledgement and increased professionalization comes on, there are things coming on the research side. I will briefly pause to plug the workshop that I'm going to be running on NDSS on SOC operations, CFP to come out soon. But we've also seen bottom up from the operational world metrics appear. One of the core things we often see people talking about is the idea of events per analyst hour. This is basically just saying this is about how much an analyst can handle in that period. And given that the term event is itself fuzzy, the standards are a bit off, but if you sort of get people in a corner, they'll say about 10 an hour. Now, the core thing here is not the 10 an hour. The core thing is that I've dealt with systems where I get 30,000 alerts every 30 seconds. So that value of EPA is dwarfed usually by what you're actually getting on the network. So, given that an attention-based framework is based around the idea that operator attention is your most valuable resource. Operators need to be creative. Attackers are a constant moving target. Things that are identifiable should be automated and moved away. And I've broken it into three basic points. The first is all security organizations are cost centers, and so they have to work within the constraints imposed by their parent organization. Given those constraints, if you're given two design options, pick the one that's going to frustrate the attacker goals more. And then given design options under those categories, pick the one that's going to let the operators manage more events. View your defenses as how am I going to be able to spend my analyst attention more wisely? If I can result in, and to sort of get onto that and what that means, let's move to the next slide. So, okay. So the history of intrusion detection follows the history of artificial intelligence to a large extent. What operators tend to be doing is validating alerts. And when I say validating, there's actually two things going on here. It's not simply a matter of false positive or false negative. There are a lot of alerts that we get that are not necessarily threatening. One of the things that I've been doing is, I've been doing analyses of the ISI dark spaces. We get, thousands of scans every day for Telnet, which, at least on the dark space, is not a significant problem for us because, we have no machines there. But the point is there's an enormous amount of undirected hostile traffic. And anyone who's directly connected, anyone who gets unfiltered email because they're running the spam filters, or anyone who's running a large network is all aware of this. What operators tend to be doing is comparing and cross-referencing data. I generally have described it as doing left joins across crappy databases. So we'll take network traffic and we'll compare it to server logs, or we'll take an endpoint agent and we'll compare it to network traffic. And these are not easy things to do because elements of identity and elements of normalcy are all a mess here. The other thing to keep in mind about this is that any network is a contested domain. Network instrumentation is unreliable. The first thing that I see most operators write for their system are systems to check the integrity of the data they're collecting because they don't trust it. And especially going back to this point I made about Leveson and crises, in a crisis, instrumentation is often the first thing to go. One of the ways, for example, in the early days that we knew that DDoSes were happening on some of the networks I was looking at was that the flow feeds from the routers stopped because flow is a lower priority process than moving packets. The other thing, of course, is if you're running any non-trivial network, parts of that network are controlled by people who are actively hostile to you. That's just the reality. We talk an awful lot about zero trust and the perimeter model is dead, but oftentimes we treat the management of our systems as if the perimeter model still existed. Next slide, please. Now, I made this point previously, but I want to sort of get into the so the classic thing in intrusion detection and anomaly detection has been to take whatever is current in artificial intelligence and plug it in there. So if you take a look, like one of the earliest intrusion detection systems, NIDES, literally the acronym is Network Intrusion Detection Expert System. If you're an IDS researcher, you have seen over the years that everything that is current in whatever we're calling AI at that point gets applied to intrusion detection. We've got Bayesian belief networks, neural networks, deep learning's being applied. And what the ops floor does is the ops floor tries to compensate for that. And the results have been a mixed bag. And there's a lot of reasons for this. Now, ultimately, what I'm sort of getting to here is what I say at the top. Anomaly detection is hard. Anomaly detection is hard because we have no universals. The internet changes over time. One of the points I make to people is, there's a lot of research where people still try to use like the 1999 Lariat data set, and like that has no relationship to what a modern network looks like. It's also true that networks in different countries, different profiles for not only the not only for the software they're running or the tools they're using, but even the types of attacks they get. I found an interesting paper about the types of scans that actually happen in different countries. Individual sites, building like deep learning models, that's doing statistical analysis with very weak power tests. There's no guarantee that an organization is going to have enough information to train a model. In particular, if you're dealing with rare and high threat events, like say spear phishing or a watering hole. The other thing, of course, is that the highest compliment paid to any effective defensive system is the attackers figure out a way to get around it. This is a moving target all over the place. The other issue is that normal traffic is not necessarily innocent. This has been a classic assumption, and a lot of machine learning work on this is that, we used to see papers where people would say we train on 2 weeks of data and work from there. As I said, I've been looking at scanning on networks for 20 years, and I see more SSH scanning than I see more SSH activity on large networks. I certainly see more telnet scanning than I see telnet activity. There's a lot of traffic where the baseline traffic is just hostile. Um, Somebody just quoted a Vern Paxson paper, which is always a good thing to do in this situation. Um, I will also say that a lot of this was informed by a paper written several years ago by Carrie Gates and Carol Taylor that talks about challenging the anomaly detection paradigm. I think it's the 2006 NSPW workshop where that was, and you can just kind of wave that like a pamphlet. The base rate fallacy, which is Axelson's particular observation that rare phenomena and commonly repeated tests, you'll just get dominated by the false positives. And then the other thing is, look, operators, go from my previous slide, operators have a limited amount of time to focus on anything. They get exhausted. And there's a final thing on top of all of this. Security organizations are cost center. They have to explain why they make a decision. They have to explain this because often security decisions are restrictive and opaque, and they make people's lives harder. Which means that if you're talking to someone and you're saying, I need to do this and I can't explain why, that has got to be a spectacular justification or it won't happen. Next slide, please, Wes. So, underpinning all of that is the idea that sort of passive machine learning driven data collection is hard. And so instead of working from the idea that we're going to passively monitor traffic and build up a model of normalcy, an alternative approach is to publish a model of your acceptable behavior for an asset and then use that information to let the network decide if it's going to allow the traffic and let the operator know what expected traffic is going to look like. So the idea here is that the contract is an envelope. It's a description of acceptable behavior, and that may include things like IP addresses and domain names. And what I use as a jumping off point here is there's a standard developed by the Luxembourg CERT called MIS, which is short for Malware Information Sharing Platform. As part of the general professionalization of the SOC floors, there's been a lot of work in the last few years towards standards for threat intelligence sharing. And what's more interesting from my perspective is that these standards are now sticking. There were a number before this, but between STIX and MISP, STIX is the OASIS standard. Um, Between those two standards, there's actual teeth to them now, and people are publishing MISP feeds and the like. So if you take a look at MISP, it's a gigantic key value store with a whole bunch of different classes of information that could potentially be stored. They're the kind of things that operational analysts are interested in. So we could do that information. And then what we can also do is we can break these into different states. The idea here, particularly for the different states, is security is about crisis. And so we need the ability to describe how the system is going to operate in a crisis. So the idea here, and so I put some basic states down here: default, what happens during a control, what I might do if there's an emergency patch, behavior like that. And then what these would do is they would describe the traffic that you could expect to see. For example, I'm antivirus software. I'm going to update my system once a day by dialing home to the update site. And one of the first things that malware authors often do, disable the antivirus software. So when I see the absence of that signal, that is for the operator a point of attention. Next slide, please, Wes. Okay. So, and basically, I just explained this slide in the last slide. So, the point here, though, the other point here, though, is to make a note that, while there are some security events where we have sort of an immediate jumping in front of the bullet situation, the most common response in a long-standing problem, and keep in mind, when we're talking about things like botnet occupations or insider threat or things like that, these are investigations that can go on for weeks or months. The most common initial response to an incident is to reorganize data collection. So you focus your attention on an affected area, or you reroute traffic. You do things so that you can look in that information in more detail and spend your analyst attention on that problem. And that's the reason to make these states explicit. One of the things I'm concerned about is, like, one of the problems we've had in general with information security is our points of control and our points of instrumentation have often been too broad. And if you go to the idea that security decisions are restrictive and unpleasant, it is in our best interest to make them as finely tailored as possible, because then what we can do is we can take a crisis, and instead of turning it into an everybody must do this now, we can more finely tailor it, deal with a very specific situation, and then move away and then put everything away again. Next slide, please. Thank you, Wes. So the general mechanism for this, I don't think at the mechanical level is a shock. The asset comes online, it publishes a contract, the monitoring system may accept, reject, or constrain it. The operational element is that the operators can use this to extrapolate behavior. So one of the common tasks that you'll see going on right now is organizations will be coordinating network monitoring and endpoint assets. So you have something like Tanium or OS Query installed on your assets, but you don't know how many assets you actually have. And in fact, the definition of an asset can be extremely fuzzy, especially when you're dealing in cloud environments. So what you'll see is active network monitoring will be used to compare, this is what the network tells me I see versus what my endpoint assets tell me I see. And then I go, oh, here's an IP I don't recognize. Let's go over. Oh, it's a printer. There's nothing I can do about that. I guess we're doomed. By publishing the contracts, what happens is the operator can do things like extrapolate behavior. I know, for example, I'm going to see a large number of updates to antivirus every day. And it provides reasons, justifications. And again, this is driven from the idea that we would be using this to monitor analyst attention or to improve analyst attention expenditure. The contracts can manage operator response by telling them this is something I'm not particularly concerned about at this point. I won't say it's safe because I'm an operational security person and nothing is safe, but it gives us a way to think about different classes of reaction. And ultimately, giving our people the ability to have different classes of reaction is going to provide more power to them. Next slide, please. Okay, so given that this is a workshop, given that we want to talk about discussions, and given that I've already seen a couple of plus Qs pop up, so let me distill this down to the core ideas and then let's talk about some questions, okay? So again, if I haven't emphasized it enough, I tend to wave around the copies of Safeware like they were scripture. Nancy Levison's work on monitoring there, and in particular the role of human in the loop, the development of expertise and the use of crisis states is, I think, very useful for us to think about here. So the idea of multiple states is, I think, important here because it's not a case of simply binary classification. There are different aberrant behaviors. And I can tell you, based on my own experience building such systems, even something as simple as detecting a threshold, you can find out that there's all sorts of specialized corner cases associated with those thresholds. The idea of analyst attention and attention-driven security, the idea that what we want to do as defenses is free up our analysts to think more about what they need to do, or what more of the problems they can face. Because look, there's an endless array of creative and hostile people out there who are always looking for new and exciting ways to mess with our networks. We can't automate against that level of creative perversity. We have to have people who are able to respond and free them up so that they can. And then the idea of supplementing anomaly detection with these explicit behavioral elements. In terms of outstanding questions, these are the kind of things I was going to ask. The idea of different types of states, what is there a dictionary of them? The question that I asked yesterday about IoT, because I've been thinking about this in particular, on a general purpose laptop, this is very constrained. For IoT, where we got largely mechanical traffic, I think there's a lot more advantage in talking about very tight bounding for there. And the question of negotiation between the assets monitoring and negotiation. And in particular, like how far do we want to go there and what are the potentials for abuse? Because, ultimately packet inspection of some kind is the elephant in the room on this. And, I can easily see an unrestricted version of this basically being destructive, which is not my goal. So, okay. Anyway, so those are, that's where I am.
All right, thanks, Michael. Appreciate it. And I think we'll have time for the two questions. So we'll start with Drew.
Hi, Michael. Michael, one query that I have, which I'm not able to understand, is especially about the traffic descriptor and this indicator of compromise. How do you detect that? Our issue is that this is all encrypted traffic, and now these things are harder to detect in the traffic. Could you explain, like, in your proposal, how do you achieve that? Like, if the data is hidden, we can't detect this thing. Even having the contract and an envelope, how does this help?
So in particular, Drew, what I'm thinking about there is monitoring across multiple domains. So let's take, for example, an indicator of compromise as a DNS name. All right. So like my sort of baseline iOS, or my baseline idea for a contract here is a system has to publish that it's going to contact an antivirus site every morning for a download. Okay. So what we would expect to see is if they're going to communicate with our internal DNS server, then that DNS server should be able to log that particular request. And then we would have to cross-correlate that information. Now, if you put a gun to my head, I will say that I think there are certain classes of traffic that I would prefer to have encrypted and not authenticated. Or, sorry, other way around, authenticated. But I also recognize that that's not a fight I'm going to win. So the classic defensive response is you have to cross-correlate across service or host-based information for that purpose. And one of the things the contract can do is it can tell you how you have to direct your instrumentation.
Yeah, thanks, Michael. So basically, I think it would mainly work when you kind of control the IoT devices, you control the network, you control the DNS, and then you can correlate. So in those kind of systems, what you are proposing could work, but may not work on the open internet and other kind of systems.
Yes, I think that this is very much.
Yeah.
I think if there's a core idea here, it is the idea of situationality. Like, I do not see this as a universal solution for the core internet. I see this in particular. I mean, I'm thinking about it now. Keep in mind, I've spent my time working on edge networks, which are pretty flipping enormous. And so that is also biasing my thought process on this. But I see this as sort of this is driven by the idea that there is a SOC somewhere that is going to be involved in the monitoring and defense of systems here. So there is that kind of concept of control, I think.
All right, thanks very much. Pedro?
Michael, thanks. I think actually what I was going to was partially addressed already, but it was more about the flexibility of these traffic envelopes and the scalability. At the end of the day, using these to monitor large-scale network. I don't know. I see. It's
Pedro,
very
you're
interesting,
very quiet. Can you speak up a little bit at all?
Sorry. You hear me or not? Sorry.
We can, but you're very quiet.
Okay. There.
It's about the same. We'll just try really hard to listen.
Yeah.
Okay. Sorry. Let's see this. There. Hi. No.
Still about the same.
You're about as good as you're going to get. Just go for it. I will
Okay,
move
okay.
the speaker close to me.
Yeah, it was just about thinking on the scalability of this approach and the flexibility actually of the envelopes to describe the different behaviors. I understand now that you are thinking on more, let's say, smaller networks, or you were thinking on edge networks of these approaches, but yeah, then thinking about the mix of these envelopes and how to actually make some sense out of the monitoring of that.
So I think that I think that the question of scalability really ties into the question of automation here. And part of this, keep in mind, is if you would ask me on Monday about this, I would have been much more heavily focused on automation. But having listened to the talks for the past few days, I think that there's this idea of a published behavioral element that's popping up in various areas. There's clearly the MUD standard, and so I think that the core thing I was thinking about for this is how do we deal with the human operator? And the answer is that a lot of the automation should be focused on reducing the information that the operator has to spend their attention on. And so what that may mean is we have an enormous number of automated filtering and controls and blocks which are intended to handle the crude and obvious elements. I don't need a lot of intelligence to tell I'm being DDoSed, and I don't need a lot of intelligence to tell that the message is spam usually. What I need to do, and if you take a look at sort of a lot of like modern detection and defensive systems, they are hierarchies of filtering and blocking. A lot of the obvious stuff will get strangled quickly so that folks at the higher end do not have to deal with those immediate problems. So I think the question really boils down to, and this is a problem that I'd really like to figure out because I think it is the core for whether this is viable and how much of it can be applied in the enterprise environment, is figuring out how much the automated versus the human role is played in this. And I've got some work on evaluating and wargaming out these situations that I'm happy to discuss offline about that, but I do think it's a core problem here. Do we have a raised hand? I thought we had yeah.
So I think we are, if there was a raised hand, I missed it.
No, my hand should be raised. Are you seeing it there?
Oh, I do see it, Fluffy. Sorry, I was looking at chat.
No worry, and I cannot put any, like you're using a 10-year-old version of WebEx if you have chat. So, yeah. I can't put anything in chat, so I raised hand, sorry. So love this talk, love this direction. And I'm very keen on this type of description of what's happening for applications that are cloud applications as well, to be able to publish and then explain to the network, or applications that were downloaded through the App Store or something. I feel like the whole IoT space is a much harder space. It's such a slow, it doesn't seem like the biggest problem we have to deal with right now. And I view this as something that can help us get some handle on detecting rapid ransomware spread, which is a fundamentally actually a much bigger issue than DDoS or spam right now, right?
Yeah.
So I'd love to see this sort of stuff. But the thing that I wanted to ask you about is really making me think was about the different states. I mean, do you view these as something that each application would pick its own idea of different states, or that sort of a standardization level we would pick, a handful of common states that all apps might use? How are you thinking about these different states and contexts?
I'll make a general point here, which is I tend to think of software as a complement to people. And so my general feeling is that instead of the software being all encompassing, let's create a baseline set of states. I mean, we've been writing and maintaining software for 60 years now, so I think we've got a good idea of what the basic set of states would be. We know we've got remote updates. We know the system might be down. I mean, we can come up with that category. And then if, for example, somebody was to march me into the IETF and start creating a standard for this, which I got nothing better to do. The base set of states, I think we could probably nail it down to maybe 8 to 10 of them. And then if we included space for additional for additional controls there. So I think that that's reasonable. I think the core question at that point becomes what the monitoring and control system actually looks like for reacting to this. I've been sort of thinking about this in the context of like talking to Zeek, because clearly that's where everyone's going these days. But there's this question of sort of, let's say, SIM/Zeek-ish interaction that I think has to be handled as well. But I can see that would be my first stab at this. And again, like I said, I go back to the sort of Leveson idea of the crisis and the role of monitoring there. So,
all right, thanks very much. We do definitely need to move on. So, Paul, you're up, and thanks, Michael, for your talk. Appreciate it.
glad.
Thanks, Wes. Can everyone hear me?
Yes, you sound good.
Okay, great. All right. Thanks, everyone, and thanks to the organizers of the workshop for inviting me to present this work and for organizing and running everything pretty smoothly. Today I'm going to be telling you about some work, some ongoing research work that myself and my collaborators are doing. And it fits really well in the kind of context of this workshop. The goal of the work is to sort of resolve these challenging tensions between like privacy and security that come up in networks that have encrypted traffic. So I don't need to belabor the context here, but just so that we're on the same page, encryption is becoming really ubiquitous these days. Using like a protocol like TLS 1.3 to use a handshake to establish a shared key, and then use it to encrypt their traffic. This pattern is becoming like super ubiquitous. And not only is it encrypting the traffic in networks, it's also encrypting the metadata like DNS. But as we all know, traditionally networks enforce policies by scanning plain text traffic directly. So the network will sort of check some policy represented by this sort of checklist here on the traffic, and if the traffic violates the policy, then it'll block it, else it'll let it through. So this pattern is like super ubiquitous in all different kinds of network management tasks like filtering and data loss prevention and intrusion detection and those kinds of things. So the motivating question of this work, which is in line with the goal of the workshop, I think, is can we sort of resolve these tensions between privacy and policy enforcement that arise in networks? So this question, at least in my community where I come from, the applied cryptography community, is very fraught because a lot of cryptographers argue that they're very sort of like crypto maximalist, and they say that we should just we should encrypt everything, and you should only enforce policies that don't require you to decrypt traffic. Whereas I think many network administrators would argue that you should only use encryption where it doesn't kind of conflict with policy enforcement. So this is kind of a very polarized debate, especially in certain areas of the IETF, like in the standardization process of TLS 1.3, there was a very acrimonious debate between network operators and the TLS working group about sort of protocol level ways of allowing these kinds of monitoring. So the goal of this work is to try to like get both of these at the same time. So before we talk about solutions, we need to sort of outline what the goals of a solution would be. The first thing we want to do is to not weaken encryption at all. We shouldn't have to downgrade encryption protocols or reveal some information in plain text or really reveal anything except to the network, except whether the traffic is or isn't compliant with the policy. And we also need to give networks the ability to enforce their policies, which in particular means they need to be able to identify traffic that isn't compliant and sort of take some action like blocking the traffic or blocking the user or something like that. And finally, we would really like to ensure that like external web servers don't need to change. So this is sort of something that needs to take place between the user in a network and the network operators, but the destination server shouldn't necessarily need to know about this interaction. And this also makes it much easier to deploy. And as a corollary, we also don't want to introduce additional trust assumptions like installing root certificates or like SGX or anything like that. And so there's been just a little bit of work in the academic community around this, trying to resolve these tensions, but all of these solutions fail in at least one of these points. So one important non-requirement that we wanted in this work is we don't want to prevent all circumvention of network monitoring because we really don't want to build a tool that can be misused for censorship of traffic. So what we want to do is allow circumvention by sort of advanced users using like Tor or a VPN or something, but is still established a sort of safe baseline that most people are going to abide by in the network. So in short, what we want to do is reveal just enough information about the traffic to allow the network to gain an assurance that the policy is being followed, but reveal nothing else. And if it sounds impossible to do this, it turns out that there's a cryptographic primitive that can come to our rescue here called a zero knowledge proof. So this is zero knowledge proof, this funny slide with Superman with the ZKP on its chest. I spent a long time making this in PowerPoint, so I just want everyone to appreciate how nice it is with the lettering and everything. So if you're not familiar, a zero knowledge proof is a cryptographic protocol between two parties, a prover and a verifier. It allows the prover to convince the verifier of the truth of some public statement. And this protocol has two security properties. And the protocol we can think of it as a single message protocol where the prover generates some bit string, which we call the zero knowledge proof, sends it to the verifier, and the verifier runs some special verification algorithm to check whether the statement is true. And this protocol has two important properties. The first is that it doesn't reveal why the statement is true. So somehow the reasoning for the statement's truth is hidden from the verifier. So this is the zero knowledge property. And second, it only allows the prover to convince the verifier if the statement is actually true. So the prover can't convince the verifier that a false statement is actually true. So this is the soundness property of the zero knowledge proof system. So with this zero knowledge proof tool, we built a solution called a zero knowledge Middlebox for resolving these tensions. So the idea of a zero knowledge Middlebox is it's a system between a client and a network and the network, or specifically like some piece of network middleware like a Middlebox. And at the beginning of time, when the client joins the network, they get a description of the policy that they need to abide by in the network. And then when the client wants to establish a connection to some remote server, they use normal encryption protocols like TLS 1.3 and just encrypt their traffic normally. But in addition to sending the encrypted traffic, the client generates and sends to the network or the Middlebox a zero knowledge proof for the truth of the public statement. Roughly speaking, my ciphertext contains compliant traffic. So if you decrypted my traffic with a key that I'm going to hide, what you get is traffic that is compliant with this policy that you gave me. And then the Middlebox can act as the verifier in this protocol and verify the proof. And if the proof verifies correctly, it gains an assurance that the traffic that's still hidden from it is compliant with the policy. And if the proof fails to verify, then it can just block the traffic or take whatever action it wants to take with the client. So this architecture, I'll just briefly convince you that this satisfies our desiderata here. The first is that it doesn't weaken encryption because we can use standard encryption protocols like TLS 1.3 combined with the zero knowledge property of the zero knowledge proof system means that the traffic is hidden, but we're still using the standard encryption protocol. So we don't have to change the encryption. We haven't weakened, importantly, we haven't weakened the encryption because of zero knowledge. So the Middlebox can still enforce policies because the soundness property of this proof system makes it so that the Middlebox, when it verifies a proof is correct, it always knows that the underlying traffic is policy compliant because of soundness. And finally, because the server doesn't even really know about this interaction between the client and the Middlebox of the network, so the server doesn't really need to change at all. So there are no changes required to the server, and the Middlebox doesn't even really need to forward the proof to the server. It could just strip it out of the connection and forward the traffic on. So building a zero-knowledge middle box, I won't sort of belabor the technical details in this talk, but I just want to convince you that building a zero-knowledge middle box is quite non-trivial. So for example, this is the key schedule of TLS 1.3, which is the newest version of TLS. And so this hideously complicated diagram is something that we actually had to digest in building our prototype. But surprisingly to us, and I hope this will surprise you as well, is that zero-knowledge proofs of properties of TLS 1.3 traffic are close to practical. So in this work, we were able to develop a proof for a DNS filtering policy that, while it's not practical yet, is within striking distance of practicality, and it's really, really on the cusp of practical. And I'll talk about evaluation a little bit later in the talk. But so I just want to pause here and tell you that if you tune out after this slide and you take away only one takeaway from my talk, I just want it to be that zero knowledge proofs are a tool that is in our toolbox for solving these kinds of challenging tensions between privacy and policy enforcement in networks. So far from being like a sort of theoretical curiosity, zero knowledge proofs are a real tool that we can really use to solve problems in real networks and are on the cusp of practicality right now. So in the rest of the talk, I'll just briefly talk about the architecture of a zero-knowledge middle box and talk a little bit about a core sub-protocol, which is like doing the cryptographic part of TLS in a zero-knowledge proof. And then I'll briefly touch on a zero-knowledge middle box that we built for encrypted DNS, like filtering encrypted DNS, and I'll talk a little bit about future work. So a zero-knowledge proof is a protocol that takes as input a public statement represented as a circuit. And this circuit is not a digital circuit, it's an arithmetic circuit, which is sort of like a circuit over a finite field. So its gates are addition and multiplication gates. But the important thing is that we can represent really any computation in these arithmetic circuits. And so we imagine these circuits as having public inputs and private witnesses. And the circuit takes these two inputs and outputs a 0 or a 1. And if it outputs 1, this means that the inputs and the witnesses satisfy the circuit. And output 0, the circuit's not satisfied. So the zero-knowledge proof protocol, in a little bit more detail, takes as input the circuit, the inputs, and the witnesses, and outputs a bit string, which is the zero-knowledge proof. And then the prover sends the inputs, which are public, and the proof to the verifier. And the verifier can take the description of the public circuit and the public inputs from the prover and the zero-knowledge proof string and run the verify algorithm, which just outputs a 0 or a 1. And if the verifier's verify algorithm outputs 1, then it's pretty sure that the original circuit is satisfied for some witnesses that the prover knows, but are not revealed by the zero-knowledge proof itself. So how do we actually build a zero-knowledge middle box, a circuit for a zero-knowledge middle box? So what we need to do at a high level is decrypt the traffic using a hidden key, which acts as the witness, and then check somehow that the plain text, the underlying plain text of the traffic is compliant with the policy. So in the paper, we introduced like a 3-step framework for this to make it a little bit more modular and simpler to understand. So we have a channel opening step, which just does the decryption part. And then we have a parse and extract step that outputs the policy relevant data from the underlying traffic, and then a policy check that checks whether the policy relevant data is compliant with the policy. So for TLS 1.3, the channel opening sub-circuit, there's an interesting subtlety here that actually, for time reasons, I think I'm actually going to skip this. If people are interested, you can ask me after the talk, but I think just for time reasons, I'm going to skip over. So the high level point here is that TLS 1.3, there's an interesting subtlety with the record layer. And the record layer of TLS 1.3 lacks an important security property for zero-knowledge middle boxes. And so we have to design our circuit in such a way that we can design around basically this lack of this key committing property for TLS 1.3. And so what we do is we take the TLS 1.3 handshake and sort of produce an initial key consistency check that the client uses to convince the middle box that it knows a hash of the session key, basically. And then when the client wants to generate a proof, it can basically refer back to this key consistency check that it did before. And so for long-lived TLS connections, this work of generating this key consistency check amortizes over all the proofs that it generates in the session. So for encrypted DNS, we built a zero-knowledge middle box. And I'll briefly describe how it works. So encrypted DNS, I don't think I need to explain how encrypted DNS works. I'll just say that by design, encrypted DNS prevents the local network from seeing what you're querying. And so it means that enforcing a filtering policy on DNS traffic in the local network is basically impossible with encrypted DNS. So this is causing huge tensions in networks. When Mozilla Firefox tried to roll out encrypted DNS by default in 2019, it faced huge blowback from a lot of technology groups and network operators and also governments, because this was going to prevent a lot of DNS filtering that people were doing in their networks. And so Firefox built in a sort of downgrade that allows the networks to sort of tell the browser not to use encrypted DNS. So by default, Firefox will actually allow the network to silently and unilaterally disable encrypted DNS, which is kind of, I think, maybe a suboptimal outcome for privacy, because it means networks have a lot of control over the privacy that the users have. So we took this as a sort of motivation and as a case study. And so we built a zero-knowledge Middlebox for filtering encrypted DNS. And so the way it works is at the beginning of time, the network creates a circuit that represents a sort of decryption and block list check policy. So the circuit decrypts the DNS query using this TLS 1.3 subcircuit I described before, and then extracts the domain name from the underlying bytes of the DNS query, and then finally verifies that the domain name is not in a set of block domains that the network creates. And so when the client joins the network, the Middlebox will give the client the circuit and the list of block domains. And then when the client makes a TLS 1.3 connection to the external DNS server and establishes a shared key, they do this normally. And then when the client sends a DNS query to the server, they include a zero-knowledge proof for this circuit to the block list, for the circuit pertaining to the block list to the Middlebox. And so by verifying this proof, the Middlebox is assured that the underlying DNS query that it can't see is not on this list of block domains. And there's a couple of details here. There's some minor differences between DOT and DOH that affect runtime a little bit. And we can actually achieve privacy for the block list with some fancier crypto at some efficiency cost. So our experimental results here for our initial prototype of the proof generation and verification are on the slide. So for the baseline circuit that we developed for TLS, the proving time was very bad. So for just setting up a TLS session, the one-time per session cost with baseline was like 94 seconds, which is humongous. So we were able to get this down to something like 16.5 seconds with our optimized circuit. And after this one-time 16.5 second setup cost, we can generate a DNS filtering proof in about 3 seconds for DOT. And so these numbers are still pretty slow. And so one goal of our ongoing work is to reduce these numbers. But we still do get a pretty good improvement over the baseline here. So in our future work, we're switching to a different zero-knowledge proof system. In the first paper, we used a proof system called Groth 16, but we're switching to a newer one called Spartan. And the proof times here are much more competitive than with Groth 16. So we see like a 10x speed up in prover time. So the work that the client has to do to open a TLS session has basically an additional 1.7 second cost, you can think, with Spartan, which is still maybe a little bit too high for some settings, but arguably this is really getting pretty close to practical, we think. The trade-off here is that the proofs are a little bit larger, but since this is a one-time cost, like a 49 kilobyte proof for every TLS session that the Middlebox doesn't even really need to store persistently, this doesn't seem too prohibitive. And after the session setup cost, we can do the decryption step of the circuit in about 0.2 of a second of prover time. So we expect that with the full circuit here, these numbers would be maybe 600 or 700 milliseconds. So think like after a 1.7 second setup cost, you can do a DNS filtering proof in about 700 milliseconds on the client. And you can verify it on the Middlebox in about 28 to 40 milliseconds. So this is the where we're at now in terms of the prover time. We're still working on building a full system here. And the full system actually kind of connecting this to the external application, there's a little bit of plumbing cost that incurs some inefficiency, but these numbers are kind of, these numbers are very promising. So we're working on this system right now and working on bringing these numbers down further. And we hope to have a paper submitted on this follow-up work like in December or so. So just in conclusion, in this work, my collaborators and I initiated a new line of work on zero-knowledge middle boxes, which use advanced cryptography called a zero-knowledge proof to resolve tensions between privacy and policy enforcement in networks. So we built an application of zero-knowledge middle boxes for DNS filtering. We also designed a couple of other applications, which you can see our paper. Here's the link if you want to see these other case studies. And we're working on additionally other case studies as well. And we're very, very excited about this work. We think like zero knowledge middle boxes and zero knowledge proofs in general as a tool have a ton of potential for kind of resolving these challenging tensions and solving these problems that arise when we need to manage encrypted networks. And so I hope you're as excited as we are, and that you think this is worth pursuing. So with that, I'll conclude and take any questions.
All right, thanks, Paul. That was fascinating, and I think it's definitely an interesting tool to throw into our toolbox. I think the first question is from Nalini.
Yeah, hi guys. So yeah, very, very interesting work. So I have a bunch of questions, but I'll just throw one in. So I think if you're talking about block lists, that's all fine and good. But the problem sometimes is you don't know ahead of time what should be blocked. For example, malware changes the URL all the time, so it's not possible to block it. You know what I mean? And so what there's a certain I guess what I can say is it seems like maybe there's a certain class of problems which may be suitable. What is your thought on that?
So the question is, if you don't know the block list ahead of time, then you can't necessarily block the traffic, like you can't block like the DNS queries. Is that
correct? You
okay,
don't
so,
know who to block. Yeah.
Right. So then if you didn't have encryption, then what would your goal be? Like, would you want to identify the domains like after they're queried?
Well, so what happens today is if there's intelligent firewalls and intelligent protection, malware detection kind of systems, what they'll do is they'll look for nonsense domain names, or like domain names which which you got in like 5 seconds ago. You know what I mean? And so that, because that's kind of the problem with block lists. I mean, there's a whole I know a little something about the particular controversy that happened with TLS-1.3, and there are reasons why people decrypt traffic. I mean, there's, as I said, I mean, this is very interesting work, and for a certain class of things, this is maybe very interesting, but there are many classes of problems. I guess, let me put it that way.
Mm-hmm. Yeah, that's true. I mean, I think we've really only scratched the surface of what these zero knowledge proof tools are capable of. And I think, to your point, is it possible to do more advanced things in a privacy preserving way with zero knowledge proofs? And I mean, I think the answer is yes. But I would just maybe need to understand a little bit more about the application to understand like what the desired behavior is. So for example, if you wanted to prevent people from querying like nonsense domains or very new domains, you could use an allow list instead of a block list and sort of give an allow list of the domains that you like, the top 1 million domains. And because of the way that these zero knowledge proofs scale, it isn't very much more expensive to generate a proof for an allow list than for a block list. So these numbers wouldn't really change if you did an allow list of like the top 1 million domains or something.
All right, thank you. Let's move on to Richard.
Well, thanks for this talk. This is really great work. The performance numbers, I think, are new since I last saw this work, so really impressive. The question I had for you, that some of the data of interest for security is in the TLS handshake, looking at things like encrypted certificates or encrypted client hello, even as some new stuff. I was wondering if you had intuition as to whether looking at that stuff might involve lighter weight zero knowledge proofs than proving things about the encrypted content, the actual traffic.
Yeah, that's a great question. The main cost of the zero knowledge proofs really is in the TLS decryption. So my sense is that the costs aren't meaningfully going to change if you are looking at legacy TLS 1.3 with like proving things about ECH. However, I think like looking at like encrypted client hello, so they're doing zero knowledge proofs about the client hello like SNI, and also like doing zero knowledge proofs about encrypted certificates. I think this is a fantastic direction. It's one that I'm actually thinking about right now. So if you want to chat more about it offline, I'd be happy to.
Yeah, I'll send you a ping.
Yeah, so that like the cool thing here would be just like splitting the enforcement of like authentication and needing to decrypt the traffic. So you could have a kind of separation of concern where you can have a system that just sort of checks client authentication, for example, without actually having the ability to decrypt any traffic at all, which is very cool.
All right, thanks very much, Paul, for your talk. Appreciate it. And we'll move on to Tommy's talk, the final one of this session.
Ready. And I'll share my screen if that's fine.
Okay. So, Paul, I think you may need to unshare my recollection.
I think it should work. You see this?
Yep.
Yep, you're good.
I'm not sharing still, am I?
Yeah.
No, you're good.
I took over. All right. I'll try to make this relatively quick. This is a simpler one. So Red Rover is something that Richard and I have been talking about for a while, and it's aimed largely at solving some of the same use cases that the last talk was covering, but in a certainly less intensive manner and a less provable manner, but something that we think may be an interesting direction for certain types of use cases. So, overall, the question that we're trying to look at here is there a conflict between filtering on a network and privacy? And certainly it seems that people have been perceiving that as a conflict as things like encrypted DNS and other things have come about. But to kind of dig into it more, I want to look at, what are the actual motivations and incentives of the different parties here, that being kind of the network operator and then the client devices and applications. So for, just broad networks, public networks, home networks, etc., the network's intent may be to block malware from being downloaded onto devices, to prevent objectionable content from being accessed, like the case we talked about on Monday of Comcast parental controls. There may be a need to enforce regulations that are required by a country to block access to certain content to particular users, or just to enforce the terms and conditions that a public network has given. And when we look at kind of the client side and the user, and I'm talking here about client devices and applications which are presumably working on behalf of a user in whatever configuration the user set up, whether or not they understand all the ramifications of that. But these pieces of software are going to be trying to protect the user security, protect the user privacy from various entities of either servers or the network operators learning too much about their browsing history and selling information, etc. And of course, the clients want to be able to give users access to the content that they want to have access to. So how much are these two sides of things in conflict? When we look at the mechanisms that we have to actually achieve these goals, on one hand, we have the network operators traditionally using things like DNS filtering or DNS redirection to get you to some landing page or block page, TLS, SNI filtering, or just firewalling IPs. And on the client side, applications are starting to use more encrypted DNS. Certainly, most kind of user-facing web traffic now is TLS protected. We expect TLS encrypted client hello to come about at scale sometime soon. That's been under development for a while. And also users may choose to enable VPNs or proxies to get added security and privacy. So at this level, we certainly do see that there can be a conflict. Encrypted DNS, as we've brought up already, can interfere with DNS filtering. The TLS encrypted client hello is directly in conflict with TLS SNI filtering, and VPNs and proxies prevent some types of IP firewalling. So at this level, they do seem like these are in conflict. However, I think when we look at it, those intents that we had originally don't inherently conflict. Sometimes they will. But for a lot of the cases of I'm just trying to do parental controls on my home network, or I have a public network at a cafe that's trying to enforce the regulations and the terms and conditions, but not necessarily need to snoop on all of my users, they don't conflict. What conflicts is the protocol mechanisms that are being used traditionally there. And these are broad statements, but I think, in general, most clients and most client applications and operating systems don't want to expose users to harmful content. They don't want to be downloading malware, and they don't want to be violating the terms and conditions that networks have. And a lot of networks don't want to interfere with user privacy and security. I think, collectively, if we could get no malware, upholding parental controls, and still having user privacy and security, that would be a good situation that both sides of this would be happy with. So for this particular aspect of collaboration, one of the things we looked to was an existing model where we have a collaborative approach for providing malware filtering or other types of objectionable content filtering. And this is something that's called safe browsing. So I imagine a lot of us may be familiar with it, but a lot of us may not be. So safe browsing is something that many, many browsers are already doing today. Most of the main ones do this. And there are a few major safe browsing services. I think the primary one is a service that Google runs that a lot of the browsers talk to. And the way this works is that there is a server-side known and maintained list of malware, phishing sites, etc., that need to be filtered out. And the browsers will communicate with that server periodically, and they will download a list of partial truncated hashes for URLs that are bad content for different categories. And this can be malware, phishing, other types of content that the browsers don't want to be able to show. And then when a browser is about to load a page or load a URL that matches one of those partial hashes, it communicates again with that server to get the more complete hash list for the bucket that corresponds to the partial hashes. And then it learns whether or not that particular URL is indeed on the block list. And then it will block that page if there's a match. So this is done and is used successfully at large scale to block malware. So the collaborative approach that we have with Red Rover is saying, can we use this model and bring it to, instead of the, browser talking to one main server, bring it to a smaller scale of just clients and client OSs talking to their network provider. And the proposal here is that essentially you need two pieces. You need a discovery mechanism by which the network can tell the client that there is this block list service that's essentially a safe browsing service. And the client needs to be able to check in to that service, which is very similar to the way that a browser today with safe browsing checks in to get this initial list of hashes. And then the second part is that there actually needs to be this filtering mechanism where this block list service essentially operates like safe browsing, and it allows a client to learn about the block list and different categories or reasons for blocking things without actually having to reveal all of the client behavior. So this is a client-enforced blocking behavior, but done in coordination and with a list that's generated by the network, that the client doesn't get to learn the entire contents of the list. So we have a lot of different building blocks that are already IETF RFCs that we could use, or things that we could modify from safe browsing. On the discovery side, we have a lot of different options. This kind of looks like it could fit into something like the captive portal APIs, where you learn extra information about a network. Similarly, there's provisioning domain options, or you could just put this information directly into DHCP or RAs. And then for the block list service, we could look at trying to standardize essentially the existing safe browsing protocol that's used. And I think there are interesting directions that could be taken to make this even more private. We could look at having longer, more complete hashes that allow you to not have to check in with the service quite as much, or look at techniques from private information retrieval. Now, with this type of approach, there obviously there can be issues for how easily circumventable this is, and also how well this works in a situation where you have clients that can be updated to work with a system like this, and also legacy clients. So since this is on-device filtering, there are trade-offs. Some aspects are actually better. When we're doing on-device filtering, and we're using a hash list like this, we can provide stronger assurances than DNS or SNI blocking alone, as long as you have a client that is correctly implemented. So a operating system that could do this can make sure that even if you're using encrypted DNS, even if you're using a VPN, even if you're using any other type of mechanism to tunnel or secure your traffic, it can still make sure that these particular URLs are not being loaded, or these particular host names are not being loaded, regardless of how they're getting there. So it can be more complete in that regard and be like truly on-device mechanisms, but with this network assistance. However, on the other hand, a malicious or compromised client could certainly cheat. It could say, oh yes, I'm doing this, but in fact not actually apply the blocking. And of course, legacy endpoints, clients that haven't been updated wouldn't know about this service. So I think the model that comes out of this is that you would probably need some sort of selective enablement. So here we have different categories of clients and then what the network will do. So if you have a legacy client, it would just continue doing traffic as normal, and maybe this network is going to apply a current policy like it has of doing DNS filtering, and it's going to block DNS encryption by doing the markers that we mentioned earlier of trying to disable what Firefox does, or trying to block other proxies or VPNs, because it wants to be able to enforce its terms and conditions or required filtering. And then you could have modern clients that could be updated for this, and they would know how to check in with the service. And likely we'd also want some sort of attestation of these devices or the software running on them, so that when we are checking in, you know, this is kind of a legitimate client doing some level of proof. And this is similar to what's already done for safe browsing, where when clients are checking into safe browsing with the Google service, they provide some proof about what version of the client software browser is being used. And that doesn't prevent all types of attacks, certainly, but it means that the bar to circumventing this is higher. So in this case, a cooperating client would check in with the service would provide the block list, and maybe the client would be either periodically checking in or checking in whatever it needs to do the block to get the full hashes. And when the network recognizes that a client is doing this and has provided enough proof, then it could allow DNS encryption, proxies, etc. And presumably, if we had some good enough attestation, then a malicious client that is trying to check into the service but not actually apply it because the software has been compromised or something like that, that could fail the attestation, and then the network would go back to the stricter stance it would have, where it filters or blocks encrypted DNS. So, obviously, this is not going to work for all kinds of networks. To Nalini's point on the last talk, there are many categories of networks here that this would not be nearly strong enough for. If you rely on a TLS intercepting firewall, for example, and you need to decrypt all the traffic, this is not good enough for you by any means. But I think there is a set of common use cases for either public networks or home networks where you're just trying to enforce best effort guarantees, where this could actually solve a lot of problems without having a huge amount of overhead, and could be maybe a lighter weight way to get to some of these things than like doing a full zero knowledge proof, etc. today. And particularly for cases where people are trying to just enable parental controls on their home network, then this probably actually meets the bar, because by the point where you can compromise the software enough that it's able to go around this, you can probably get around a lot of things anyway that these current network and DNS filtering mechanisms are vulnerable to. So in summary, we believe that fundamentally filtering content and user privacy do not need to conflict, and we can have collaborative solutions that work in the situations where the networks and the clients and the users have goals and incentives that all align. That's not always the case, but we do believe that exists in many cases. And mainly the gap here is that we need to talk about more standardized protocols to enable these collaborative models. And there are ways that we could do this that aren't a huge amount of effort and new work. So we believe it's achievable. And that's all I have.
Awesome. Thank you very much, Tommy. And so I think the first question is from Paul Grubbs.
Thank you, Tommy. This was a really cool talk. I'm wondering, so it seems like the proposal is like roughly moving safe browsing closer to the edge, right?
Right. I mean, maybe it's, I think you could have either a model where there's a safe browsing service essentially that runs like very close to you in the network, or your network points you to the safe browsing service that it wants you to apply, which may be one that's shared across many different networks.
If I can just pop in here real quick, I would clarify that it's not just about having locally closer to the edge, but also having the edge network have the ability to have a say over what's in the list. So it's not just one global list; it can be specialized per the local provider's needs.
That's right.
Yeah. So I'm just wondering, like, the really dumb solution to this problem is to just basically treat. So you have a safe browsing service, but all it is a cache of the safe browsing URLs plus whatever the network wants to add. And then clients just download a gzip of the list when they join the network, right? And then
of the actual list to block.
right.
So, I mean, yes, that's also kind of the initial thing that I had proposed in some of our conversations around this. I think the twofold concerns there are these lists can be quite large and quite dynamic. Oftentimes they would be larger than you'd want to just download and store on every device. And there's also a lot of concern.
Oh, sorry. I was just going to ask, do you have like a number, like in terms of the number of URLs?
I'd have to look it up, but it was, yeah, I think if you wanted to get the full list of URLs, I don't know, it's, half a gigabyte or something, like, larger than you want to just have every client always downloading. And I think the other aspect is, particularly with normal safe browsing, due to how dynamic this is, there is concern with just having the entire list be published, because then it'd be very easy to just keep generating names that are not on the list. Like it's very much an arms race of, a new bad site pops up, it gets on the list, they try to, once they learn they're on the list, then they need to modify their names. So I think certain use cases of just like, oh, you need to block these 100 URLs, you could just give that list, and if it's not a sensitive list, you could share it. But I think there are use cases where we need to have it be a bit more dynamic.
Okay, I have follow-ups, but maybe we'll take it offline.
Yeah, why don't we take it to the main discussion later? That would be good too. So with that, Patrick.
Yeah, hi Tommy. That's a really interesting talk. I suppose really for clarification, safe browsing as implemented by the Safe Browsing API only deals with URLs. What you're potentially suggesting here is something that's going to intervene necessarily with the DNS resolution process. And bearing in mind also with safe browsing that you could have perfectly reasonable content on a website, but also have within that same website having a page that's been dedicated to a phishing attack, and that's those two things can coexist. Can you clarify if you're going to be sort of intervening with the DNS resolution process as you currently envisage it?
Yeah, I mean, I think the proposal here is that we would take what is currently a URL browser-based thing talking to a server and make it a real OS service in which, if we know full URLs, yes, we can have those too. But I think, yes, filtering even just on domain names at the DNS resolution time and essentially hook this into getter info on all of the devices and just operate there would be the proposal.
I actually think this is one of the cool things about this proposal is that unlike, say, filtering in a DNS resolver, a safe browsing filter, at least the way safe browsing is applied today, operates on a full URL. So you can do precisely the distinction you're talking about, Pat, where you allow innocuous parts of a domain name's web content, but block the malicious parts. And all of that can be done even before DNS resolution, before there's any interaction with the site, just based on vetting the URL the user has entered.
Okay, thank you. I look forward to finding out more about this very interesting proposal.
All righty, I think that's the cue.
I think that is the cue. All right. So thank you, everybody, to the 3 invited talks and the really wonderful questions. At this point, we would like to just have the larger discussion, both about this day in particular. And I think, I'll say, why don't we just roll all 3 days into a single topic at this point as well. Is there people that want to discuss, how do we get from hearing all these talks, to actually making progress and making movement in this space? I think the proposals today are certainly interesting. Are they actionable? Are they, usable and things like that? Does anybody have comments that would like to throw into the queue at this point? Uh-oh. So, I mean, one of the, let me seed it a little bit then. I think one of the common themes across all three of the presentations had some scalability issues. Scalability from, Michael in terms of the level of things that could be handled, scalability that, Tommy just talked about with both the size of the data and the dynamic nature of it, which actually I think is one of the things that makes me worry about MUD and things like that is behaviors change, and how do you prevent an actor from getting in the middle of that and publishing a new behavior, or behavioral analysis in general have always led to way too many incidents of compromise or signals and things like that that just overwhelm the operators that Michael was talking about in the first talk, for example. And that apparently worked. So, Richard.
Yeah, it looks like you got a few entries in the queue while you were advancing. So I wanted to kind of expand on Tommy's thoughts a little bit and kind of throw a question out to the network operators in the crowd. The premise of something like Red Rover is that there is collaboration there in the sense that the filtering system only works if both the network filter provider is working properly and if the client properly applies the filter. So the question, and at the same time, it seems like these mechanisms are mainly worth building if they let you dial back on some other security mechanisms. Say you might allow VPN connections out of your network from a host that agreed to apply your filter in this safe browsing sort of scheme. So the question is, from a network operator point of view, is that actually a trade-off anyone would be willing to make? Would you be willing to dial back some of the protections that you're applying today, be a little less paranoid in terms of enforcing things in the network, in exchange for offloading some of these functions to the client, trusting the client to do the right thing?
Whoops, sorry, mute. I'll leave it to somebody to answer that. That's a very good question. Rob?
Yeah, I won't answer that question, but I think it's an interesting question. So I really liked, can you hear me okay, boy? Am I audible?
Yes, I hear you.
So I really liked the Red Rover presentation, and I liked the thing of Richard's presentation yesterday in terms of it being a collaboration between the network and also the user of that network, that effectively both of them have needs, and it's trying to get the balance between those two needs, both of the network and the user. So I like that. I think the one key question I have on my mind is that this ETH draft is coming along at some pace relatively quickly. And my question is really about timing of these sorts of mechanisms to have this sort of selective filtering or something. Should we be allowing ECH to progress to the point of being standardized before we have these mechanisms, or should we be trying to ensure that these mechanisms are available before we go the full hog to ECH? Is my question.
All right. Always tempted to answer networking questions because having worked in both sides, it's always a strain between users and networks. I think the multiple questions around, is there a balance that both sides can agree to is kind of fascinating. Nalini?
So I'm going to pull back a little bit and think about the question of two questions. What have we done, and where are we going, and what's the problem? And I think the problem is this is a very large problem, and I don't think we even have a scope for it. And because there's multiple different kinds of implementations. I mean, there's the wider internet, there's the IoT world, there's private managed networks, and then the other problem of very targeted solutions versus some kind of overarching solution. I mean, correct me if I'm wrong, but I don't see like a really overarching solution. Possibly the some of the stuff with the P4 or maybe zero knowledge proof. I have to think a little bit more, but everything is very limited in scope. And is that there's no question that that's certainly a route to go down, because I have to think what is practical. And in some senses, the last presentation from Tommy and I believe Richard Barnes, that's a very practical and probably doable solution, because there's a limited number of people who need to implement it. And I believe probably one of the people who could implement it is a co-author. So that's probably a plus right there. So there's going forward, because there's a bunch of questions here. And so I guess my question is, where are we going with all this?
Excellent question. Tommy is going to answer it, right?
Well, I was just going to try to give 2 cents to what Nalini was asking there. I think it's a very good observation that there doesn't seem to be an overarching solution. I don't think this space will have an overarching solution. I think if we look at the previous stance with unencrypted traffic, we had everything was just kind of out there and available. And so you had the DNS to look at and filter or modify. You had the TCP connections to look at or modify or block. And in that, the kind of the input, while that was all uniform, the things that people do with it was hugely different. The different techniques people had for filtering and blocking or modifying or optimizing their network, there were a lot of different approaches, but they didn't have to coordinate on them because all of the information was there. And so it seemed like one simple space that now is disrupted, but really there were many different things. So I expect, as we have more encryption, and if we want to have explicit collaboration, we realize that there are 20 different use cases and different things that networks want to do to manage it. And those may each have a completely separate mechanism to support it. So like in the Red Rover case, it's like, how do we solve just this, block the things I'm required to block by regulation or parental controls? And that can be one mechanism. And the mechanism for doing zero rating or optimization on a network or other things like that can just be a completely different one. And I guess that makes more work for people writing the standards and doing the things, but I don't think we'll have one solution that will fit every network and every use case that they need to apply.
Paul Grips.
Yeah, kind of following on what Tommy asked, I'm also wondering, like, Nalini, do you think, to your point, do you think it would be useful to try to come up with a proposal for some kind of holistic privacy-preserving managed network architecture? I mean, do you think the concern I have is, like, if someone proposed this is like, would it be so general that no one would ever use it because it would try to solve every problem, and in doing so actually solve no problems? Or do you think like some kind of proposal for a more unified view of this would actually be useful, I guess?
If that's for me, I can go ahead and answer. Well, okay. So I do have some thoughts on a unified structure. Of course, my problem, and we can talk, I mean, maybe I'll talk to Miria and some of the other folks offline, but it's encumbered. And so that makes it problematic, I think. Of course, maybe not. I mean, and again, there are thoughts. I have had some thoughts on a more unified structure. The problem, though, it's so there's two things, right? There's one, what is a possible re-architecture? And then two, who will actually do this? And then we have to live with the realities of, will Cisco cooperate with Microsoft and Huawei and Apple? Well, you know what I mean? There's the there's the practical solutions, and then we have the problem of non-greenfield implementations. Anytime you propose a holistic architecture, it really needs to be transparent and seamless. Otherwise, it's not going to get implemented. And so that's kind of my path. I don't know if that's any, I think, I don't know. I can certainly talk to people offline about encumbered solutions and whether that is of interest. Just my 2 cents. Yep.
Thanks. Let me interject sort of an example I was thinking of earlier. I think one of the reasons why what people are describing is difficult, right? The different places that you might need to deploy something can be very, very different in what they need. I mean, if you think about the solutions that we've talked about today, enterprises want to be very strict in what they allow in and out of their network, and they have legal reasons for doing so, you know, both for data leakage as well as, you know, potential lawsuits. Whereas home users actually want to be protected, and those two different types of scenarios have very different end goals that, you know, firewalls and things like that have been able to generically do before. And there's a question of I think that people are bringing up of those two use cases are quite different. So I'll just throw that out there as examples people may or may not want to talk about. So Dhruv.
Thanks, Wes. I kind of agree with what Tommy and you guys are saying, but at the same time, during this discussion also, I do realize that, like, for instance, the title of our workshop, like the whole network management itself is such a vast topic. And then when people use terms like, okay, how do we don't decrypt or do this particular solution, I think we need to be much more specific on where we are applying the solution, for what kind of network and for what kind of use cases. And when we use a generic term like network monitoring, it just leads to more confusion. So one of the outputs that I could think from this workshop is, whenever we are thinking of this, we do try to categorize and come up with sort of a framework or a categorization of, these are the various different use cases where we categorize the network monitoring into things that we talked today, like, you know, the block list one, safe list one, TLS and DNS. All of this are different, and malware, they are so different from each other. So we do need to categorize them and say where they need this common security properties, and then for what kind of network would they be applied to. And then if we have that kind of categorization, then when we have a conversation in IETF and otherwise, it's easier for folks to understand each other and where they are coming from and where a particular solution do apply. And even if the security properties are so different for different use cases, then having an overarching solution automatically sort of becomes a difficult task. And that can give us an idea that, okay, maybe we need to think about an overarching solution, or better to go for each use case and like each category of a use case as a different solution. My last point was, like, after the day one, we did not hear too much about the AI stuff as much. So I wanted to hear from other people as well. Do they still think that the AI-based solutions are viable, or they are not? Thanks.
Thanks. Yari?
Yeah, thank you. So maybe I'm repeating a little bit of what other people have already said, but I guess I'm agreeing with Nalini that there's like a big space out there, both in terms of solutions, even problems. I think if you're trying to optimize something, you're trying to debug something, you're trying to express your preferences, you're trying to filter something. These are different things, and we should, at least not in my opinion, assume that there's one solution that solves all of them, and we should not chase that path. So if you find a nice solution for a particular part of the problems, then we go for that. For instance, some of the filtering things today were quite interesting and probably fruitful avenues for research. Also wanted to try and answer Richard's question, like would the network operators be willing to do this trade-off if they were able to do filtering but not be able to look into packets? I think that's a complicated question because there's probably many deployment situations. But if I speak about the public operators, my perception at least is that they probably would be willing. They would be able to provide a function and even some server equipment to provide some of the lists and facilities for that, and get the thing that the users actually want executed and done. So that's great. But there might be some other situations where that's not as easy. I don't know about enterprise, for instance. That could be a different problem, or maybe not. Maybe others can comment on that. Also, governments sometimes put requirements on other people and other entities, and good governance, I guess, should be technology agnostic, so that if you can do it with DNS-based filtering or some more clever trick with zero knowledge proofs, for instance, then both should be fine. But in reality, that's not always as simple as that.
Sure.
Yeah, I'm kind of just agreeing to Yari here. So like my one takeaway is that there's not like one solution that fits everything. We have to go on a case-by-case basis, but the good news is there are a bunch of solutions. And I think like when we have a case and we find a solution, then we can learn something from it, and we can maybe apply a similar approach to different problems. So what we could do is look at the solutions that we have here and figuring out what are the patterns, what is different from what we do today, and how can we apply it to other problems maybe as well. But it's probably a one-by-one study, and it's a lot of work, and that's why we have this workshop here. And then very quickly, I wanted to reply to this other point Yari also was talking about. So the content filtering, this is mostly done by network operators because they have legal obligations to do so. And so, they would need a very strong proof that this is done correctly in order to fulfill their legal obligations. But if you look at what Tommy presented effectively, you don't need the network operator in this picture, right? Because why should the network operator provide you a block list? Why does the network operator know anything about the content? It's only this way because of this legal obligations. So, I mean, if the legal obligations would change and it would not be the operator who has to do the blocking, but the operating system, you don't need this step at all. So this is the dilemma we have here, and maybe also something to consider.
Thanks, Miria. And thank you, Richard, for mentioning that Colin is in the queue.
Thanks. I was just trying to think of what we could pull out of this as sort of steps forward, and it seems to me that a lot of the proposals we've had so far group broadly under a category of things that are, like Michael Collins sort of, work out that it's from the application describing what it needs up. And some of them are from the idea of the network having some sort of list of, adult browsing or type thing or something like that that's coming down, and the network can pass it on down to it, and ignore the up and down things, but just the two different ends here. And I think that we should approach this from both directions simultaneously with small, simple solutions to it, the simplest ones we can, and they won't be perfect, and we'll have to make, many small incrementals. And it goes back to what Tommy was saying about this problem was previously solved with a lot of different ways that came together. They might have used some common mechanisms, but they were actually very different systems to that. We shouldn't be bothered by, we have solutions to parts of this problem that slowly fit together to make a broader solution over time. So in particular, I would be very excited about seeing some work that helped applications describe what they used on the network so that could be used to help filter network events and better understand what they did. I think that'd be great work to have. And then broader ways of describing both block and allow lists, not only block lists, and having in the network and having the network being able to describe those lists in some compact way, being able to bring those into policy enforcement points wherever those are, and some way for the network to communicate, those types of things. I mean, I think if we had better solutions to all of that, those would all be good things for us to work on and coming out of this workshop as sort of both directions. Thanks.
Thank you, Colin. And I put myself in the queue in part to respond to the AI related question earlier. And actually it follows really nicely onto what Colin was just talking about the need to have both block and allow lists and figure out a way to mix them. When you have AI and machine learning related techniques, you have to consider what the actions of those will end up being. So I'm doing research right now into doing traffic identification to allow network prioritization of particular flows. And so you can say, oh, well, this flow is, quite possibly an interactive SSH channel, and therefore you might want to prioritize, its latency over, some video channel that is being buffered or something like that. But the important thing is the end use case, right? If you accidentally have a false positive and you prioritize some flow that didn't need that priority, nobody's really going to complain, right? That's very different than if you are trying to use a technique in order to create a block list where you're going to deny something and you let something through that shouldn't be, or more, or equally as problematic, you actually block something that needed to get access. I mentor at a high school all the time, and the high school has decided to have a rather expansive block list that blocks things that the students actually need. And I understand it, but I mean, they block DuckDuckGo, but not Google. I mean, it's like the decisions don't make a whole lot of sense all the time. GitHub is actually, they had to ask for it to be released every year because the students use it heavily. So when you end up having those two use cases, there's still got to be some negotiation for how does a client, add or remove their needs individually, I think, which is also multiple people have talked about. So. With that, I think the next person in the queue is Paul Groves.
Yeah, so I just had a question about going back to the question like Miria brought up of like regulation. I was just wondering, people who have more experience with regulation, I mean, is it the case that when the regulations dictate like content filtering, does the regulation say the networks have to decrypt traffic, or does it just say that they have to enforce content filtering? Because seemingly, if they only have to enforce it, then some kind of client-side solution would work. But if they actually are legally required to decrypt, then there's really nothing we can do. And so as a follow-up question, like where people think it's feasible to like talk to regulators and sort of explain these privacy solutions to them. I guess I'm just wondering, like, even if we develop the best privacy solution in the world, if the regulators don't understand it and won't do it or use it, then like if the regulations don't allow it, then it's a moot point. So I guess I'm just wondering where people view like the regulatory environment as being.
It's a good question. I think we are at Nalini.
Yeah, no, I'd like to hear Paul's question answered too. There's, as far as I know, there's a bunch of different regulators. But what I wanted to come back, I want to, I'm a little conscious of the time too, and thinking about next steps. I like a number of the ideas. I think Dhruv brought up something, and Yari. One concrete output that might be interesting is what are the environments that we're talking about, and what are the kind of problems that are solved today and that probably need to be solved tomorrow. The problem, of course, is like we are a small subset of people, and it's hard to know, within ourselves if we all know everything that's being done. So maybe a crowdsourced approach to like people throwing in is like, what are all the things that you need? I mean, what do you do for diet? I mean, and you can be roughly categorized, performance monitoring, diagnostics, malware detection. I mean, you can at least categorize that. But if at least we know that, like, okay, we've got 6 concrete environments we need to deal with, and they have X specific characteristics. IoT networks are like this, by and large, or whatever. Enterprise regulated networks are like this. The wide internet is like this, or something like that. And then have another list of, okay, so what I need to do is I need to detect malware. I need to diagnose problems of X kind. I don't know if that is of use for us to have as an output.
Thanks, Delaney. I think there's a number of people that have brought up sort of a need for definitions or classes of realms, defined in what they are. It's almost becoming like a terminology need, which is an interesting thing. So thanks for bringing that up. Torles.
I think what I'm missing overall is I haven't seen, any statement in the IETF about the need to support with appropriate IETF technologies the need for securing not only the privacy aspect but also other interests that we feel we want to support, right? So do we think we do not need to care about how parents can protect their children from abuse in the internet or according content, or equally enterprises protecting their content and access to their network, right? So I think that malware was brought up, right? So all these things, I haven't seen a good statement of the IETF about it. It just seems that we're never getting out of our corner of saying privacy above all else, and that just means that what I'm seeing is there is an even worse ramp up of the different interest groups, right? So, for example, the more we encrypt on the network without providing any form of way to build policies to do this, the more I see the intrusiveness against the privacy of the users go into the endpoints, right? I mean, endpoints are having all these, in enterprises, are having all these terrible MDMs that are so intrusive, right? That are kind of reaching into every application, doing stuff, allowing, the fascists in whatever department and enterprise they are to inspect everything. And so I just don't think we can win it. We're just moving the picture out unless we actually have a broader set of goals that we are following to do something in the IETF besides just privacy. I mean, the fact at all that, the whole concept of a firewall has no official representation in the IETF. We just, acknowledge it's there, but we have, no plan about it. The only plan we had at some point in time was behave, right? So I think that's really, I think, at the core of the problem.
All very good points. I think one of the things, since the queue seems to be empty, minus some plus ones to what people have said, I think one of the things that I would love to hear is, given all of this, it seems like there's a few people that have come up with a number of small ideas for going forward and things like that. Is there anybody that wants to propose, some thinking that you've gotten out of this? We could turn to sort of some brainstorming on things to do next, and actually maybe even build some collaborations. Or does anybody have projects that they're working on that they want help with or want collaboration with and things like that? Given either the papers, hopefully people have read more of the papers than just what the talks came out of today. Does anybody want to speak up toward things that they might want to do, or projects that they might want help with, or new things? I mean, I think the one that I mentioned already that multiple people have talked about is maybe some framing and terminology would be a good thing for multiple people to get together and co-author something. So Torles again.
Yeah, so I mean, I was bringing up on Sec Dispatch this discussion where Mark also chimed in with respect to. I really liked what we had before TLS 1.3 came in, namely being able to know kind of in a somewhat cryptographic fashion whom you're talking to by looking at the server certificate, right? So that solves, I think, a lot of requirements. Of course, it's not doing it well, right? So it was removed because it provided intrusiveness. So the question is really, could we come up with a cryptographic scheme that would allow to have a three-party relationship where, you know, a client will learn, okay, you need to allow to see what is the authenticated certificate of the server you're talking to, but that's all, right? So not being able to intrude on the content, have the privacy on the content, but being able to have filtering based on, you know, a firewall authenticated certificate of the server, right? So at least, you know, it would be, I think, a cool cryptographic and session establishment problem to solve. Then, of course, comes the whole question, is this a useful compromise, which goes back to my prior statement that we don't have any, you know, IETF position on that beyond, you know, yeah, everything needs to be protected from any third party. So yeah, that's what I would, because it's hard, and you know, I wouldn't know all the cryptographic aspects to make a three-party transaction like that work well.
Can I just inject here with a brief response?
Sure.
I just want to observe that the objective of having filtering applied by the network, like one of the core points of both Red Rover and the Zero Knowledge Middlebox work, is that to do filtering in the network, you don't need to expose to the network all of the names of services that people are connecting to. So I think that's a property that we should aspire to in any work that's done in the in this kind of next round of collaborative solutions.
Well, I would say that that may be a good solution for some problems, but I don't think it's the correct solution for all the problems, right? I think that would be a longer, I'd like to raise a counterpoint on that. I mean, we are using authentication for everything that we do want to talk to. Why don't we want to use authentication for, you know, decisions made on policies about whether or not somebody is allowed to talk?
So the point of both Red Rover and the Zero Knowledge Middlebox work is that the information that is being used for the policy decision is in fact authenticated, and authenticated, at least in the Middlebox case, to the network. But the network does not, through that process, learn who is being connected to, only that it is an allowed host.
Sure, but I mean, then it goes back to where do you derive that, is it allowed or not, right? And I'm saying that a very simple way to do this is by being able to know who you're connecting to, right? By cryptographic certificates. If you insert another policy layer that basically says there is another, you know, complex entity that decides whether or not that's allowed to hide the identity of the service you're connecting to, like classifying them, that's fine, but that's an even, you know, more complex solution.
Yes, I mean, the solutions you're talking about are quite simple, and that's why they've been done for so long. The problem is that they don't meet the security objectives of modern applications, and that's why we need to add the extra complexity.
I think one of the fundamental tenets that we are struggling with in this work is trust, right? We've talked a lot about trust in these different cases of, does the network trust the user? The flip side of that is, does the user trust the network? And sometimes it's nice when those are all, we trust each other, but in many adversarial networks, in coffee shops and things, you know, you probably don't want to trust the network, and the coffee shop probably doesn't trust you. And finding solutions that work, you know, across all of those, I think, is one of the things that Nalini was saying would be hard to do. It'll be challenging to do that. So I think at this point we have drained the queue. Lots of good, interesting discussion. Do any of the other chairs or Miria, or I guess any other IAB members, want to ask some follow-on questions for things that we could take out of this? Certainly the IAB thanks everybody for participating in this workshop. It's been valuable to at least learn and come up with you know, topics and things that we know, you know, need to be worked on.
Yeah, maybe I want to at least add that I think it was like, for me, it was very useful to see all these inputs together in one workshop and have the discussion. I'm not sure if we have any concrete follow-up items rather than just keep working on the stuff somewhere in the IETF. But that's not a too bad outcome of that. So I also hope that like not only the people in this workshop share this experience with me, but that we can also produce a report that provides this experience to people outside of this workshop.
Excellent. Okay. Anybody else have closing thoughts and comments? All right, hearing none, I think that we'll go ahead and close. We are, 3 minutes from the top of the hour. We've managed to time these perfectly every day. I don't know how in the world that happened, but the discussion has definitely petered out at just the right time. So I'd like to thank everybody, and as I said, the AIB thanks everybody for participating. This has been fascinating. We will probably send out mail at some point about if there's, if at some point this will turn into a workshop RFC for a report. I've taken lots of notes, and we will also look at the recordings and things like that. So you should be hearing from us again. Great. Thank you, everybody. And we will solve this problem one day.
Thanks, guys.
Thanks, everybody.
Yeah. Bye.
Bye.
Bye.